Hi everyone, welcome to the Chapter 3 review video. We are going to be going over concepts of probability, the fundamental counting principle, permutations, and combinations. I'd like to show you a couple of shortcuts on the TI-84, so if you have your graphing calculators handy, get those out and try and follow along with all the different keystrokes, and I'll show you some different functions that you may or may not be aware are on your graphing calculator. Let's go ahead and get started. Number 1 asks us how many 4-letter television call signs are possible if each sign must start with either a K or a W. This question deals with something called the fundamental counting principle. The fundamental counting principle says that if event A can happen M ways and event B can happen N ways, then the number of ways that events A and B can happen together is M times N. Now, essentially, this is what's going to happen in this problem because I have 4 events. I have 4 letters to fill in this television call sign. There's only one stipulation. The first letter for each sign has to start with either a K or a W. So there's only 2 options to enter that first letter. Everything else, could be any other letter of the alphabet, which there are 26 of them. So we fill in 26s for the other 3 letters of our television call sign. So 26 cubed times 2 will be 35,152. That will be B. Number 2, the spinner shown is spun 1 time. Find the probability the spinner lands on blue. Well, this is an example of classical probability, right? The number of ways that an event can happen divided by the total number of ways it could happen. So the number of times or ways that it could land on blue, there's 3 ways that can happen out of a total of 8 possible sections on this spinner, means 3/8, which that is 0.375. Number 3. The bar graph shows the cell phone provider for students in a class. One of these students is chosen at random. Find the probability that their provider is not AT&T. Okay, well, we know that one of our probability rules is that the sum of the probabilities has to be 1. So, for instance, the probability that some event A happens plus the probability that some event A does not happen, and we denote this by a little apostrophe symbol, A prime, event A does not happen, the sum of the probabilities has to be 1. So this is a simple equation. If I solve for any one of these things, all I have to do is use my balancing rules from math class and do a little subtracting. So if I want to find the probability that something does not happen, this guy, if I want to find that, that means I have to subtract away the probability that it does happen. So the probability that something does not happen is 1 minus the probability that it does happen. So in my example here, the probability that some student does not have AT&T is going to be 1 minus the probability that they do have AT&T. So this is going to be equal to 1 minus, well, the probability that they have AT&T is 16 out of a total of what looks like 40, right? 5 and 7 is 12, plus 12 is 24, plus 16 is 40. So the probability that they have AT&T is going to be 16 out of 40. Okay. So we go over to the calculator, do this out using parentheses on our fraction. 1 minus 16/40ths will be 0.6 B. Number 4. One card is selected at random from a standard deck, then replaced, and a second card is drawn. Find the probability of selecting 2 face cards. Okay, this question is asking me about the probability of events happening in sequence, which uses what I call the AND rule. Okay. Now, this breaks down into essentially 2 options for us. It depends on whether or not the events are independent of each other. Now, we say that 2 events happening in sequence are independent if the probability of the first event happening does not affect the probability of the second event happening, in which case the probability of of event A and then event B happening is just going to be the product of event A times the probability of event B. Now, we say that two events are dependent if the occurrence of the first event does affect the probability of the second event happening, in which case the probability that event A and then event B happens is going to be the probability of the first thing times the conditional probability of the second event. Now we read this notation right here as the probability of event B happening given that event A has already happened. So this line right here, this line that separates B and A, we interpret that as the phrase given that. So the probability that event B happens given that event A has already happened. So in this situation, I first want to ask myself, okay, I know this is something happening in sequence, two events, one thing happening right after the next. My first question to myself should be, are these events independent or are they dependent? Well, I know that after the first card is drawn, it's replaced, right? It's put back in the deck. So whenever the second card is drawn, it's still out of a standard deck of 52. So these two events are independent of each other, right? Because of that replacement. The first card is selected randomly and then put back in the deck. So it doesn't really matter what was drawn on that first card. It's going back in before the second card is drawn. So I know that I'm working with this formula, this AND situation. The probability that event A and then event B happens is just going to be the product of their probabilities. So let's work this out. The probability that we draw a face card and then we draw another face card. Well, this will be the probability of drawing a face card times the probability of drawing a face card. Now, how many face cards are there? Well, there's 3 in each suit and there's 4 suits, so that's 12 face cards out of 52. That's the probability on the first card that is selected. That card is replaced in the deck, so there are still 12 out of 52 face cards for the second draw. So we want to do 12 50-seconds times 12 50-seconds. And that's 0.053. So 4 is B. Number 5. One card is selected at random from a standard deck, not replaced, and then a second card is drawn. Find the probability of selecting 2 face cards. Okay, so this is again the AND situation. 2 things are happening in sequence, but in this case, the first card is not replaced. So that means that the second card's probability of happening has been compromised. The sample space is no longer out of 52 cards, now it's out of 51 cards. So we have to use the conditional probability formula. So the probability that A and then B happens is going to be the probability of event A times the probability of event B given that A has happened. So the probability of drawing a face card and then another face card is going to be the probability of drawing a face card times the probability the second card is a face card given that the first card is a face card. So for the first card that is drawn, we still have that classical probability of 12 out of 52, right? This is the first card that's drawn from the deck. Now, that card is not replaced. So for the second card that is drawn from the deck, we have to assume now it's out of 51 because that first card is not replaced. I also have to consider this conditional part of my probability that the first card drawn could have been a face card, right? We don't know what it is going to be beforehand, but after it's drawn, it's not going back in the deck. So I have to account for the fact that potentially now I'm at 11 face cards left in the deck. So 12 out of 52 times 11 out of 51 is going to give us 0.049, which is going to round up to 0.05. So 5 is A. Number 6. The table shows the favorite pizza topping for a sample of students. One of these students is selected at random. Find the probability the student is male given that they prefer pepperoni. So let's practice that notation again. probability of being male given that they prefer pepperoni. In a table situation, the given that portion of the problem kind of solidifies or isolates a particular row or column. So we're really only concerned with people in general that prefer pepperoni. So I'm already kind of focusing on this column. Given that they prefer pepperoni, what is the probability that the student is male? Well, 5 male students out of a total of 9 students preferred pepperoni. So the probability here that you are male, given that we're already assuming you prefer pepperoni, is going to be 5/9. 5/9. 0.555 repeated, so that's D. Number 7, true or false? The following events are mutually exclusive. Okay, well, let's first just review, what does it mean to be mutually exclusive? That means the outcomes of each respective event do not overlap. You are mutually exclusive if there is no overlap in the outcome of the events. So, event A is being born in California. Event B is watching American Idol. Are these two events non-overlapping? Well, no, they do overlap, right? Let's think about a Venn diagram picture here. Let's say that this circle is being born in California, and let's say that this circle is that you like American Idol, right? I'm sure there is a person out there in existence who is a native Californian and also watches American Idol, right? These two circles are overlapping, right? So they are not mutually exclusive. So we would say that this is false. They are not mutually exclusive. There is overlap there. Number 8, the table shows the favorite pizza topping for a sample of students. One of these students is selected at random. Find the probability the student is female, probability that a student is female, or prefers sausage. Okay, well, this is not a question about things happening in sequence. This is a question about multiple outcomes occurring on a single trial of a probability experiment. Multiple outcomes occurring on a single trial of the probability experiment. This is the OR probability formula. It goes something like this. The probability that event A or event B happens is the probability of A plus the probability of B minus the probability that there's some overlap there. Okay. So in this case, the probability that you are female, that's event A, or the probability that you like sausage, event B, is going to be equal to the probability that you are female, which in this case is 9 out of a total of 24, 9/24, plus the probability that you like sausage, which is a total of 5 out of 24, 5/24. Now, there is overlap here, right? Because we have 3 females who prefer sausage, right? Those 3 females got counted in the gender total, and they got counted in the sausage total. So those 3 people have double representation in this probability formula. We don't want that. We want everybody to have equal representation. So we have to subtract the overlap. That's essentially what we're doing right here in this part of our probability formula for an OR situation, the probability that A or B happens. If you have certain outcomes that have double representation, you need to subtract away the overlap. So that's what we're going to do. We're going to subtract away those 3 females that prefer sausage that got counted in the count for female and got counted in the count for sausage. Okay, so let's go ahead and calculate that. 9/24 plus 5/24 minus 3, whoops, I don't know why I have 25 there. Silly Katie. This is out of 24. Minus 3/24. 0.4583 repeated, so that looks like A. All right, number 9. There are 15 dogs entered in a show. How many ways can first, second, and third place be awarded? first, second, and third place. Okay, this is a permutation, right? Because if we're talking about places in a race, first, second, third, I cannot simultaneously be first place and second place, right? Once first place has been awarded, then there's only going to be 14 dogs left over that could enter in second place. Once second place has been awarded, there will only be 13 dogs that could enter into third place. So you could do this a couple of different ways. You could say, this is like the fundamental counting principle. I've got 15 options for first place. Once that's awarded, I've got 14 options. Once that's awarded, I've got 13 options. And we could do 15 times 14 times 13. That's a total of 2,730 different ways of awarding first, second, and third place. We might also recognize that this is a permutation kind of problem. I've got n things that I'm trying to fill R places. Your calculator will calculate permutations very quickly and very easily for you. This is how we do it. NPR. You enter in the total number of ways that something can happen, and then you enter in the total number of positions that need filled. So in this instance, I've got 15 dogs, and I want to permute them into 3 different spots. So in my calculator, I type 15, and then we hit the math button, and we scroll over to the probability menu, and it is the second option down. So I'm going to hit 2. And then you enter 3. So 15 things, permute them into 3 different spots. That's also going to give me a total of 2,730. So either method is going to work for you. I kind of like that the calculator does permutations quickly and easily. You don't have to memorize the formula that's in the textbook. So just a handy little trick there for you to use. Again, this is under the math button. Third button down on the left-hand column of buttons, math, and then scroll over to PRB. That's the probability menu. All right, last problem, number 10. There are 13 students in a club. How many ways can 4 students be selected to attend a conference? Okay, so how is this problem different than the one that we just did? In this case, we're not talking about a permutation here. Order doesn't matter. In the previous problem, order did matter, right? First, second, and third, how those things are awarded are different depending on which dog actually comes in which place, right? So let me scroll back up here real quick. So saying that Fido, Petey, and Spot were first, second, and third is a different outcome than to say Spot came first, Fido came second, and Petey was third, right? It's a totally different outcome to the race. So in number 9, order mattered. That's what made it a permutation. In this situation, in number 10, I can get down there. In number 10, we're talking about just 4 people in a group, right? The way that a group of people attends a conference doesn't matter, right? Whether we say that Kim, Ben, Allie, and Alex attend the conference, it's not any different to say Alex, Kim, Ben, and Allie attend the conference, right? Just because I list the names in a different way doesn't make it a different group, right? In this case, we're just talking about a collection of people. So this is a combination. And again, your calculator will do combinations for you. So we're trying to take 13 things and make a combination of 4 of those items. So we're literally going to be entering this the same way that we did a permutation, except now we're denoting that order doesn't matter. So in the calculator, you're going to type 13, and then math, scroll over to probability, and it's the third option down here, NCR. So 13, put them in a combination of 4 items chosen from that group. There are 715 different ways of choosing 4 out of 13 students to attend the conference. So that's going to be D. Okay. Now, one thing that was not covered in this video was the distinguishable permutations, right? Whenever you have multiples of a certain item and you're trying to come up with unique ways of ordering it. We also miss some of the finer details of the different and or rules and the complement rules. So make sure you go back and make a list of possible formulas to use for your exam, and really go through the review homeworks to help yourself prep for it. Obviously, if you have any questions, please let me know, and I will see you in the next video.